An Introduction to Forces. There's a lot of vocabulary in this, so let's get to it. Mass is the property of a body that is a measure of its inertia, and that it is commonly taken as a measure of the amount of material, or matter, it contains, and causes it to have weight in a gravitational force. Mass is measured in kilograms. Inertia is the resistance to change. Center of mass is the single point where the weighted positions of all parts of an object or system balance to zero, representing its average position. It's also where gravity acts. Forces are vector quantities, pushes or pulls, that describe the interactions between objects or systems measured in newtons. Newton spelled out as lowercase. In an abbreviated form, it's capital N. Could also be kilograms times meters per second squared. A contact force is an interaction between two objects or systems touching each other. A field force is an interaction without contact. Free body diagrams are useful tools for visualizing forces being exerted on a single object or system and are used to determine equations that represent a physical situation. Net force is the vector sum of all forces exerted on the system. Equilibrium is a net force of 0 newtons in all directions. This is the Greek letter capital sigma, used to signify the sum of. This is the Greek letter lowercase mu, like the Pokemon, and it is used to represent the coefficient of friction, which is a unitless ratio of an object's weight to the normal force applied to it. Normal means perpendicular to a surface. So what is a system? We're going to think about a system like a football team on the field. In football, you've got players with specific roles and positions. They work together, pass the ball, make tackles, execute plays according to a strategy. For us, a system is similar to this football team. The players on the football field are like the components or the pieces within our system in physics. We carefully select and define which objects are part of our system for a particular study or analysis. Just as a coach chooses the players who will be on the field for a game, we choose the objects that are relevant to the physical phenomenon we're investigating. Now consider the plays and strategies as the interactions and behaviors of the objects within our system. The players' movements, passes, and tackles are like interactions between the objects in our defined system. We study these interactions to understand how they contribute to the overall game. The overall game that we care about is the physical process we're interested in. And just like there are rules to the game, in physics we have rules of the universe, or physical laws, to analyze how the objects within our system behave and interact. So in physics, a system is like a football team on the field, where we carefully select and study the players and their actions to understand the dynamics at play. Or in other words, it's just the stuff we care about. If the properties or interactions of the objects within a system are not important in modeling the system can be treated as a single object. We've seen this when we used the particle model before, and we used kinematics and the negligence of air resistance with projectile motion. We look at things for the macroscopic view in this class. You can also look at it from the microscopic, and physics is going to be the same no matter where you are or what level you're looking at it. That's the beauty of it, really. The internal structure of the system affects the analysis of the system. If you've ever tried to put together a poorly manufactured puzzle, you know all about this. If the little pieces don't fit together just right, the full picture is hard to see. In physics, you can't properly analyze a situation if one important component is missing or ignored. How can we properly analyze the friction between tires on the road if we're not including the tires on the road in our system? To identify our system, we're going to start by drawing a dotted circle around the system, especially in the beginning until you get used to the idea of defining a system. We'll name our system with the major components like this. A road tire system would be the system where we're analyzing the tires on the road. Mass and inertia. So which is more difficult to get started moving or to get to stop moving? Toy car or a real car? It's obviously going to be the real car, because the real car has more inertia, and because inertia is a resistance to change motion, which means moving, stopping, rotating. We can also say the more mass an object has, the more inertia it has. This is called the inertial mass. There's another type of mass called gravitational mass, which is determined based on the amount of gravitational interaction an object has with another object. We're going to talk more about this later in the class, but I wanted to bring this up so you know there's two types of mass, gravitational mass and inertial mass. In a lab, in experimentally shown to be the same quantity. This should be the case, otherwise physics as we know it breaks. This is called the equivalence principle, and it's a key tenet of Albert Einstein's general relativity, which is the warping of space-time based on an object's mass. We don't get to talk about Albert Einstein a lot in this class, so I wanted to touch on that. The center of mass, again, is a single point where the weighted positions balance to 0. For systems with symmetrical mass distributions, the center of mass is going to be located along lines of symmetry. And symmetry just means that we can make a change to the orientation without changing how an object looks. The location of a system's center of mass along a given axis can be calculated using this equation. X center of mass equals the sum of sigma m times x divided by the sum of m. We can't just cancel out the sigma m's here because sigma's, first of all, not one of our variables. It's a mathematical symbol that tells us it's the sum of. So if we have multiple objects, this would be like adding m1 times x1 plus m2 times x2 divided by m1 plus m2. We can't cancel those out. System can be modeled as a singular object that is located at the system's center of mass. So that means taking the whole entire system and shrinking it down to a point, just like we've done before with the point particle and the particle model. Forces are vector quantities. Vectors are arrows with magnitude and direction. They represent interactions between objects and agents. An agent is the thing doing the forcing, and the object is the thing being forced. The unit of measurement is the Newton. Again, can be shown as kilograms times meters per second squared. The tool that can be used to measure forces are scales and force sensors. Either of these are going to measure the force that the sensor or the scale exerts, not the force that's being exerted on them. What that means is if you stand on a bathroom scale and you look down at the reading, the scale is not telling you how hard your body is pushing against the scale, but instead how much the scale is pushing up on you. Here I want to list through a whole bunch of forces. We've got the force name, which tells us what the force is, the symbol, the equation, if there is one, a clue to help identify in these certain situations and phenomena, the agent of the force, and the direction this force points. We're going to start with a weight force, and the symbol is Fg or Fw, and the equation is m times the gravitational field. The clue is if we're in the vicinity of a gravitational field. The agent in this case will be the planet, that's the thing doing the forcing, and the direction will always be down, towards the center of the planet, or sun, or moon, or anything. Weight is a force, which is a vector, while mass is a scalar quantity. Mass does not change when you move to another planet, weight does. Notice the Fg equals mg, and that little g changes depending on where you are. When you go to the moon, you're not dealing with a g equals 10 meters per second squared anymore. Now you're looking more like g equals 1.67 meters per second squared. So you weigh different amounts based on where you are. Next up we have the normal force, and that's the clue here is going to be an object is in contact with any kind of surface. The surface could be one book on top of another book, one box on top of another box. Book against the wall would be the surface. In the other examples, the books were each surfaces. So the agent will be whatever the surface is, and the direction will be perpendicular to the surface. Even if it's at an angle, normal means perpendicular. So the perpendicular to the surface will also be at an angle. Our next force is the tension force, F sub t, which the clue here is a string or a rope is part of the system, and the agent will be that string or rope. The direction is going to be the direction the agent is pulling, because you can't push with a string or a rope. So you have to imagine a string is always pulling. Next up, we have our static frictional force, F sub F, or F sub F sub S. We have two equations for this. The first one is the absolute value is less than or equal to the absolute value of our frictional force is less than or equal to the absolute value of our static coefficient of friction times our normal force. And the second equation is our frictional force, the maximum frictional force, equals our coefficient of static friction times our normal force. You can use them interchangeably. It's not going to affect anything mathematically, but it's important to know that when we're dealing with a maximum force required to overcome static friction, we're dealing with static frictional force. Other clues would be an object not sliding, the word rough being present, non-negligible friction, maximum force required, traction. All of those clues tell us there's friction involved. The agent in this case will be the surface, and the direction will be the opposing sliding. Even if an object is not sliding, you have to imagine what direction would it be sliding in. Friction would act in the opposite. Next we have kinetic friction, F sub F, F sub K. Here, two more equations, F sub F equals the absolute value of mu K times Fn. Remember, absolute value just means magnitude. Magnitude just means absolute value. So there's not going to be negative here. Our clue here is that there are objects sliding relative to each other. It could be a box sliding relative to the floor, or a box sliding relative to another box. A lot of boxes in this unit. Our agent here is a surface. Direction, again, for friction will always be opposing sliding. Next we have our elastic force, or spring force, F sub S, and that X as our equation. Our clues are if there's a spring or if there's rubber within the system, anything that has any sort of elasticity to it. The agent will be that spring or rubber, and the direction will be back towards the resting point, or back towards the equilibrium point. We have our applied force, which is not used all that often. We use F sub A for that, and we're only going to use this if a hand is in contact with the object that we care about. So our agent will be a hand, and the direction will be in the direction of the push or the pull. One more, drag force, F sub D. Here we have two equations based on their size. Fd equals negative bv, and Fd equals negative bv squared for larger objects. Our clue here is whenever we're dealing with air resistance, this is how we do it. We treat air resistance as a force. Our agent is going to be the air molecules, and the direction will always oppose the motion that an object is going through. On to net force. Net force is the sum of all forces, sigma F or F net. Forces are vectors, so direction's important. A useful phrase worth remembering to determine net force is the net force equals the stuff that makes it go minus the stuff holding it back equals ma. Or the net forces are positive forces minus our negative forces. I like the stuff that makes it go minus stuff holding it back because that's going to be universally used throughout the year. We can use it whenever we're talking about net any vector quantity, whether it's torque or displacement or velocity. This is Newton's second law of motion. If an object is speeding up, slowing down, or turning, that means there is a net force. There is a net acceleration. Newton's second law in equation form is our system's acceleration equals the net force divided by mass. Newton's first law of motion, if an object does not speed up, slow down, or turn, all of the forces are going to cancel out. Mathematically put, our net force equals zero. This means there is zero acceleration. We call this state of motion translational equilibrium, whenever our forces all balance out. If an object is launched into space with a speed of 10 meters per second, that object will move forever with a constant velocity of 10 meters per second. Conversely, if an object is laid on a table, that object will stay on the table, if left undisturbed, forever. Newton's first law is also known as the law of inertia. Inertia is the resistance to change. Forces may be balanced in one dimension and not another, the x and y. So you could be completely balanced in the y direction, but not completely balanced in the x direction. That means you're accelerating in the x direction. If there's an unbalanced force, there is an acceleration, which is a changing velocity, in the direction of the unbalanced force. An inertial frame of reference, that is a frame of reference that is not accelerating, can be used to verify Newton's first law. If you're in an inertial frame of reference and you observe an object with no forces acting on it, you will see it either at rest or moving at a constant velocity in a straight line. That's you sitting in a car, moving at a constant velocity. Everything relative to you is not moving. You may have already guessed, to represent forces, we're going to use arrows that have lengths proportional to the magnitude of the force and point in the same direction, or point in some direction. Let's consider a box on a frictionless table. First, we're going to define our system as the box table system, dotted line around it. Next, we're going to draw the force vectors to represent the forces acting on the box from where they're acting. Here, we're going to start with the easy one, which is the weight force, which always points down. Next, we have a surface, so we have a normal force coming from the surface. This is called a force diagram. There's certain situations where it's useful, usually when we're dealing with rotations. However, for us, there's a condensed version of this method called free body diagrams. When we remove all of the components of the system and concentrate only on the center of mass, for the object we're looking at, we can model the center of mass as a dot or a square. As you can see, the forces are leaving the center of mass and are pointed in the direction they're acting. The weight force is pointed down while the normal force is pointed up. Rules for free body diagrams: first of all, make sure you label all forces. Always label your forces. All arrows must start from and point away from the center of mass, the dot or the square. All vector lengths must be proportional in length to the magnitude of the force they represent. If two forces are in the same direction, draw those forces side by side, not on top of each other. Only full vectors, not components, will go on the free body diagram. If a force is unbalanced, there's a changing velocity in that direction. Remember that stuff that makes it go minus stuff holding it back equals mass times acceleration. Here's an example of not being in translational equilibrium. Now we have our forces balanced in our y direction, but not our x direction. From the free body diagram, I can write my Newton's second law equation. One equation for each dimension. One for the x and one for the y. Stuff that makes it go minus stuff holding it back equals mass times acceleration. So in the y direction, stuff that makes it go is our normal force, minus stuff holding it back is our weight force, equals mass times acceleration. And in the x direction, stuff that makes it go, our tension force, minus stuff holding it back equals mass times acceleration. There's nothing holding it back, so minus 0. And we get those two equations. Last example, and this is one with a force at an angle. Because the vector is at an angle, we have to resolve it into its x and y components, but we don't do that on the free body diagram. So I've redrawn our vector to show the components. So in the y direction, the stuff that makes it go minus the stuff holding it back, Fn sine theta, minus Fg equals 0. Stuff that makes it go in the x direction is going to be tension minus Fn cosine theta equals m times a in the x. There's your equations without all of the spaces. Next, complete practice drawing free body diagrams. For more practice, there's your AI prompt. Ask each other, ask me, and keep asking until you get it.